So let's look at applying Bayes' theorem to localization, or figuring out where you're at in a space. And this is obviously normally applied to robotics. So the first example I'm going to do is kind of a simple one where we're kind of assuming that we know things for a fact, 100% certainty. So first, though, let's say, or when I say 100% certainty, I'm talking about events that are happening. So what that means is, we'll start out and we're in this 5x5 room, and we don't know where we're at. We just got plopped down there. We could be here, we could be there, we could be anywhere. So that means our probability is distributed across this entire space. Our sample space is all 25 of these cells. So the probability that you are in this space is 1, right? All of our probabilities have to add up to 1. So what that actually means is if you want to assign a probability for each space, we can do 1 divided by 25. So that means that's a 4% probability for each of these spaces. And just to double check things, what we can do is we can scroll over this whole thing and we can see our sum adds up to 1. So that means that we approach that problem right, because we should always have our whole probability of our space equal to 1. So that was our initialization. And now let's say a robot knows its orientation. It knows if it's facing north, west, east, or south. So let's say that the robot is able to move north 1 space. Actually, just to really highlight things, let's say it moves north 2 spaces. So it moves 2 units, or we'll say units. It moves north 2 units. So, what does that mean? Or what can we do with that information? Well, we know, let's think of kind of some extremes here. If we started out here, and we moved 2 units, that would put us here. If we move 2 units, that means it would be impossible to be at this space, or really this row or this row, because you would have to have started outside of the room, which we know we did not do. So that means that now there's a 0% probability that we are in this row or this row. So what I'm going to do is I'm going to kind of say we know we're in this area, and really we have a probability of 100%, or we'll say 1 that we're in there, and then so that means this zone is a probability of 0. So what can we do with that? Well, we can scale this according to Bayes' theorem, and we can say we know we're in this area, so now we basically need to scale each of these probabilities to reflect that, right? That these are no longer possible, but these areas are now even more possible. So to scale that, the first thing we need to do is get the sum of this whole space for our previous probability distribution. So that sum is, I can see, is 0.6. So I'm going to remember that. And our probability that we're in this area is 1. So what I can actually do is I can take equals, so the probability that the robot's at that location, our probability that this event actually happened is 1, so it's kind of useless, but I'm going to put times 1 in there. And then I'm going to divide by the probability of this whole region, which was 0.6. So that now means the probability of the robot being in this area is now 0.07. And so I'm going to scale that this way, and then I'm going to scale that this way. And now, likewise, we can apply that here, where if I sum up this turns out to be 0.4. And so I know we know this is going to turn to 0, but so we've got our value there times the probability, which is 0, divided by this whole summation, which was 0.4, and it turns out to be 0 as we expect. So I'll scale that to these guys. Now, here's always the great double check that you can do with probability. Because of our second axiom that everything adds up to 1, what that allows us to do is select this whole space, and if we did our stuff right, we should see that our sum is 1, which is what happened there. So let's just apply this one more time. Let's say we move east 1 unit. So, and we do that with absolute certainty. So now that limits our space to here. So that means this is a probability of 1, and what's left is a probability of 0. So let's apply this one more time here. So we're going to first, I like to do my kind of positive or my true space first, but the order doesn't really matter. So here my denominator is going to be 0.8. The sum of all these probabilities is 0.8. So what I do here is this equals the previous probability times 1, right? Because the probability of this event happening is 1. It's certain is what that means. And our denominator was 0.8. And now it looks like we can take this guy and scale it. Alright, so that's the positive region. Now let's do this guy, which is, well, let's add up what this is just to find it. Alright, so all these are 0, so that means the denominator is 0.2 there. We know it's going to turn to 0, but that's alright. So it's going to equal this times 0 divided by 0.2. Sure enough, turns out to be 0. And we can scale it this way as well. Alright, and let's just double check that and make sure our probability is 1. It is. Yeah, so that was kind of our first example of how I run through problems like this. And this is just kind of a stepping stone to doing kind of more advanced methods for localization. This is just kind of really understanding the idea, or how you can apply Bayes' theorem to kind of start deducing where your robot might be. Right, so we started out thinking it could be anywhere in here, and then we moved around, and that kind of has limited us to knowing that we're probably in this area. And obviously your robot would have some more like sensors that might say, hey, we crashed into a wall, which would give us a much greater certainty that we were up against a wall, and stuff like that. And that's what we'll look at in the next example.